Azam on recently recognition of the Vice Chancellor Teaching Excellence Award. So over to you, Haniya. Congratulations.
Thank you very much. That just puts me under a whole lot of pressure to perform. Thank you very much for giving me this opportunity. What I'm going to do today is just share some work that that I've been doing in collaboration with Christian Blanchet. And yeah, this is basically a report on what I've learned and on what I have been interested in past few years. So yeah, so I'm going to talk about topological Fukaya category of Riemann surfaces, and this is a topological variant that we propose, which we think is very nice because it's very intrinsic to the manifold, to the surface. It's very topological, very intrinsic model. I'm going to give a very, very possibly oversimplified account of this. So yeah, if you're already familiar with most of the things that I say in my talk, please excuse me for making it sound all too simple, or maybe skipping a few gory details. Okay, so yeah, so basically, where does this all fit in? So there's this very active and exciting area of physics, which is called string theory. And there's this phenomenon of mirror symmetry, which was observed by physicists, in which you have a manifold, let's call that X, and a certain geometry on that manifold somehow is reflected in a different kind of geometry on another manifold, which we call the mirror to X. So these two are mirror to each other, and we denote the other one by X check. So the symplectic side is usually referred to as the A side, and the complex geometry is generally referred to as the B side. And this mirror symmetry is a phenomenon which I said that was initially reported by the physicists. And I will give you some idea of why this took mathematicians, in particular geometers, by storm. So for mirror symmetry, there was a mathematical formulation given by Kontsevich in 1994. And it was called homological mirror symmetry because it's at the level of categories. And what this means is that you have a category on the A side. So whatever this is, I'm going to explain what this is in this talk. This is the protagonist of the story. And this is equivalent to the category on the other side. So this one is the bounded derived Fukaya category on X, and this one is the bounded derived category of coherent sheaves on the mirror manifold. But I'm not going to talk about this one. All right, so here's an outline of my talk. So I'm going to talk about some preliminaries just to motivate what we're doing and why it's interesting, and why, a whole lot of other people are doing this. Not specifically this, but they're interested in this, the homological mirror symmetry conjecture, collecting evidence, and there's a whole lot of interesting mathematics coming out of this. And I'm going to talk about floor theory on our manifold of interest, which is going to be a Riemann surface. And we're going to talk about Fukaya category. And finally, I will, just mention one main result, the paper. And yeah, that's about it. Okay, so let's start with the first thing that I want to talk about in preliminaries is comparing the two geometries, so symplectic manifolds versus complex manifolds. So let's look at Kähler geometry first. So Kähler manifolds are, if you know what a manifold is already, if you're looking at a real manifold, then locally it looks like Rn. It's an n-dimensional manifold, then locally it looks like Rn. And if you're talking about a complex manifold, then locally it looks like Cn. And Kähler manifolds are a special class of complex manifolds, which come equipped with a compatible Riemannian metric. And the geometry of such manifolds is Kähler geometry. And there are a couple of familiar examples that we can think of instantly. So for instance, we can think of the complex projective space itself, CPN. And as a matter of fact, any projective variety is also, so there's a Riemannian metric, which is called the Fubini-Studi metric on CPN. And basically the same gets restricted to this variety. And so it gives you a compatible Riemannian metric. Okay, so just to be more concrete, CP1 is just this sphere, and this is a Kähler manifold for you. So Kähler geometry, just for the sake of information, has very rich local detail. And this will be clear when I talk about the symplectic side of things. So let's move on to symplectic geometry. So symplectic geometry is the geometry of an even dimensional smooth real manifold, which comes equipped with a non-degenerate closed two form. So it's a closed two form. Let me give it a name. Let's call it omega. And if you start with a 2n dimensional smooth real manifold, then omega n, which is basically just omega wedged n times with itself, this thing is non-zero. So that's what it means for it to be non-degenerate. And it's closed. So if you're already familiar with forms, differential forms, you must be familiar with an exterior derivative. So if you take the exterior derivative of omega, then you get zero. And that's how you say it in words. You say that it's closed. So it's a closed non-degenerate form. And non-degeneracy is equivalent to the fact that basically you have this isomorphism between vector fields. So here you have the tangent bundle on, oops, I switched to M all of a sudden. I should also change this. Let me call this, I don't know. Let me call this Y. Bad notation, but please excuse me. I don't know why I switched to X all of a sudden. This is Y, and this is still my manifold X. Okay, so you take the tangent bundle, and the section of the tangent bundle is going to give you a vector field. And here you see you have a two form omega, and this I is basically contracting the two form with respect to this vector field and giving you a one form. All right, so that's the formula. That's how you contract. And this is a one form. It takes in one input from the cotangent bundle, and it gives you a real number. All right, so what are the examples? So if I look at R2 with coordinates x, y, we can consider omega naught. So the reason I didn't call it just omega is because this is how you denote the standard form, symplectic form, which is omega naught. This is just dx wedge dy. And here you see this isomorphism at play. You see this one direction is, it corresponds to this contraction, which is the form dy, and the other direction corresponds to this contraction, which is minus dx. So this means that for R2, all you have is omega naught is just the area form, dx fetch dy. So in general, this is true that if you have this pair, an even smooth real dimension, even dimensional smooth manifold, it admits a volume form, which is equipped with, of course, a non-degenerate closed to form. It admits a volume form, which is non-vanishing, which is loaded twice. Get rid of that. All right. So, right. So, but what's the contrast with Kähler? As I said, Kähler has very rich local detail. The contrast is that locally, this geometry symplectic side is not so interesting. The reason is this theorem of Darboux, which says that every symplectic form is locally diffeomorphic to the standard form on R2n. So you take any symplectic manifold, its symplectic form will be locally diffeomorphic to R2n with the suitable, the standard form on R2n. And so this basically just means that symplectic structure does not give you much local detail, but it offers more interesting global structures as opposed to local detail in Kähler. So there's a whole lot of contrast. And in higher dimensions, the local picture is still a little interesting. So for instance, you have a non-squeezing theorem of Chromo. This is a nice picture. I took it from an article and I forgot to write down the reference, but this is not my own picture. This is really just, the theorem really just is a mathematical or symplectic geometric formulation of this phrase that says that you cannot pass a camel through the eye of a needle. And then you have symplectic rigidity and other results like the Arnold's conjecture that I'm going to mention later on. Okay, so you see a whole lot of contrast between Kähler and symplectic geometries, and mirror symmetry in physics gave these geometers some evidence of a connection between the two. And these two facts took the world of geometers by storm, and there began this work on mirror symmetry or mathematical formalism. There are a whole lot of different formulations. There's SYZ mirror symmetry and other sorts, which are purely mathematical and subject of great, very interesting research. Okay, so I've been using the word category because the key word is Fukaya category, and I need to tell you what a category is, primarily because you've already seen categories before, even if you didn't know the word. So what is a category? A category is just denoted by this curly C. It has two aspects or components, if you like. It has objects, which we denote as objects C, and it has arrows, which we denote by morphisms. And examples, the first easy example would be that of a set. So if you start with a set, the objects, the category is, so the category here is the category of sets, and the objects are basically sets, and their morphisms between two objects, S and T, are just functions. So you've seen this category before. Then we have this category mat, which has objects that are just natural numbers, 1, 2, 3, 4, 5, and morphisms or arrows between them. So this is another way of writing arrows. So I can also say that this arrow is there. This arrow has this definition. It's the set of all M cross N matrices. And that's where the name mat comes from. Okay, so this is categories. And then you can look at any pre-ordered set, such as, let's say, R with its usual order. And here again, the objects are just going to be elements, which are basically real numbers, if you're talking about R. And arrows between two real numbers is just going to be given by the order relation between the two. So this formalism basically just very abstractly, it covers all sorts of examples, you can think of, like considering a set as a category, the category of sets as a category, and so on and so forth. So there's a way, there should be a way for, two categories to speak to each other. And that's where we need to define what a functor is. So a functor is a map between two categories. And again, since categories have two aspects to them, objects and arrows, so you need to define these functors at the level of objects. So that's at the level of object. That's at the level of object. So I took two objects, C1 and C2 from C, and D1 and D2 from D. And you have a map between objects. And here we have these vertical maps or arrows inside the respective categories. And this assignment is basically at the level of arrows. So it maps an arrow to another arrow, but at the other category. So just to give you an example, we can keep considering the preordered set as a category. So I'm taking two preordered sets. So these are two different categories. And this, a functor between them is just an order preserving map. So you can imagine taking two different preordered sets, and a map between them is as simple as one imagines should be. All right, so what about the equivalence of categories? So as I stated before, so I'm just in the preliminaries, I'm just trying to, I'll take you back to this again, the homological mirror symmetry statement, because it asks for an equivalence between two categories. Yeah, so I need to also quickly just give you an idea of what an equivalence between categories is. So there's also a notion of isomorphism between categories, like you've seen in the case of vector spaces in linear algebra, when two vector spaces are isomorphic, if and only if they have the same dimension, like finite dimensional vector spaces. And you may have seen the notion of isomorphism in group theory. And similarly, you have a very rigid notion of isomorphism between categories. So you have a map this way, you have a map another way, and then you have these compositions which are identity and so on. So this really means that they're the same. So for example, if you've seen module theory before, then you can consider the category of left R modules, R is a ring, and the category of right R modules. And both of these are really exactly the same. So you can define a map going from one to the other, and they compose to give you identity. So that's really being the same, but that's not what we're interested in. We're interested in a more flexible kind of an equivalence, which says that they are essentially the same. And that's what you call equivalence of categories, okay? And basically that involves the fact that it's full, it's this functor, there exists a functor F between the two categories, it's full, faithful, and it's isomorphous dense. So maybe I don't think I can go into the details, but if you already have some idea, then you can say that the home set, which is a set of all homes between two objects, their restrictions are all surjective, that's made full. Faithful has something to do with injectivity, and so all home set restrictions are injective. And isomorphism dense means that for any object here, any object D here, you can always find an object C here, so that it gets mapped to something which is isomorphic to D on the other side under F. Sorry, I wanted to say it's isomorphic to D. So that's isomorphism test. So for example, if you take MAT, which was this category of with objects which were natural numbers and morphisms that were given by the set of all matrices M cross N, this one is equivalent to the the category of vector spaces. So it's easy for you to guess what the category of vector spaces would be. So objects would be vector spaces, and morphisms between two objects would just be linear maps between those two vector spaces. So that this thing is equivalent to the category of finite dimensional vector spaces. So maybe you can, yeah. Okay. And then you can look at another example, which is the category of metric spaces with continuous maps. This is equivalent to the category of meteorizable topological spaces. So, but the first one is interesting because you can, we can just instantly check that this is equivalent and not isomorphic, because you have, well, maybe an easy way to say this would be that you have a notion of, isomorphism between vector spaces, objects inside the category of vector spaces. But here you only have integers or positive integers, and there is no way to have any equivalence between two different positive integers. So that they cannot be isomorphic as categories, but they are nevertheless equivalent. All right, so back to homological mirror symmetry. So Kontsevich in 1994 gave the homological mirror symmetry conjecture, which is a mathematical formulation of the mirror symmetry conjecture that the physicists, so there was a phenomenon that physicists observed, and then they made this conjecture, which is for mirror symmetry. And then this is basically just the mathematical formulation of that. I have a problem with these arrows going both ways because it's really not going both ways. Maybe I should just draw it this way. Okay. Right, so you have a manifold X on one side, the symplectic side, and a mirror of that on the other side, the complex side, and you have this equivalence between the two categories. So this DB is, so B stands for bounded and D stands for derived. So this is just the derived, bounded derived Fukaya category of X, and this is the bounded derived category of coherent sheaves on the mirror. Okay, so maybe I'll speak later what derived means when we're doing the growth interior. Okay. So any questions so far? If there are any questions, I'd like to take them, but you can interrupt me anytime. I'll try my best to answer your question. Okay, if not, so we can continue. I can't see the chat, so maybe you'll have to tell me if there are any questions. All right, so what is the Fukaya category after all, and why are we interested in? So as I said earlier, this is basically this work takes inspiration, I must mention, from Muhammad Abu Zaid's work in on Fukaya category of higher genus surfaces. So let me just write that down. And so this takes inspiration from that. And the difference, one big difference is, of course, that he considers the symplectic geometry in the sense that it considers the area of form and the contributions that come with it, whereas we disregard the area of form, and so we're suppressing the analytic side of things and making it purely topological. And for that, we need to make some arrangements so that things still work. And that would be the admissibility condition that I will introduce soon. so that things can be counted, that you need to count, and the sums are finite, and so things are well defined eventually. What I just said makes not much sense, but when we see later on, I'll give you the definitions and you'll see what I mean. All right, so why are we interested in this? So there's this very nice, there's a conjecture of Cooper and Samuelson in, about which basically feeds into this very new Hall algebra approach for skein algebra of a surface relative to its boundary, and and having intervals on the boundary. So so it basically just says, maybe I can just so the graded, let's say graded Homefly PT skein algebra is conjecturally equivalent to the Hall algebra of the Fukaya category of the surface. So this X before is now a Riemann surface for us. Okay. And I'll say that in a minute. So anyway, so this is a subject which is interesting for people who work on lower dimensional topology, or in particular knot theory, and and also anyway, so that's kind of motivates us to work on this topological model, because for them the analytic details are not very important. In fact, they're quite overwhelming. Right? They kind of take over the subject matter, because of course they're important and they're really at play, but it kind of it's not really the area of people who purely work on topology. And so that's one motivation why I'd be really interested, but apart from the fact that it's really interesting. Okay, so maybe we can start with floor theory. That's the second part of my talk. So floor theory is going to be part of the Fukaya category. So I need to tell you what it is. It being very, very brief. I mean, So at the risk of oversimplifying things again. So this was invented by Andreas Flohr to solve Arnold's conjecture. So Arnold's conjecture states that any self map for a symplectic manifold, for a smooth manifold, should have as many fixed points as critical points of any smooth function, as critical points that any smooth function on that manifold should have. And there is a branch of mathematics, which is, well, not really a branch, but there's an area of mathematics which is called Morse Theory, which gives these bounds on the number of critical points that any smooth function on a manifold must have. And these are, really governed by the topology of that manifold. And so this floor theory is just an infinite dimensional analog of Morse theory. And we're interested in really Lagrangian intersection floor theory. I'll tell you what that means in a moment. Has many flavors. There are, several, there are like a sequence of 2 books written by Fukaya, Ono, and Ota, and of course, several other authors, which I'm not, this is not exhaustive, of course, many flavors. So I need to come back and to what, we want to talk about, really. So for us, X is a Riemann surface of genus greater than or equal to 2. So it's just genus higher than 1. And this is what it looks like. So this is a genus 2 surface, a 2-hold torus. This is a genus 3 surface, and so on. So we want it to be connected, we want it to be oriented, and we want it to be compact. We want to say it in one word, say it's a closed surface. And so this is the Riemann surface X. It comes equipped with an area form. It's a smooth, real, even dimensional manifold. It comes equipped with an area form, and this is actually symplectic. So what are Lagrangian submanifolds? So symplectic manifolds admit some special submanifolds, which are called Lagrangian submanifolds. So this is just a symplectic manifold, and L is a submanifold. It's Lagrangian if it satisfies the two conditions. So the symplectic form restricted to the Lagrangian is 0, which means if you're familiar with isotropic subspaces, then this just says that L is an isotropic subspace. And the dimension of L is half of that of X. So these are isotropic half-dimensional manifolds, submanifolds of X, which are called Lagrangian submanifolds. In physics, string theory, we generally call them branes. And this is maximal. There's a way to show this, that these are in fact maximal isotropic submanifolds with respect to omega, the symplectic form. All right, so let's look at X, this R2N. So this X and Y are now have like N coordinates in X, N coordinates in Y. And this is what the standard symplectic form looks like. And you can take this Lagrangian L in X, which is basically just Rn, half-dimensional, with just one set of coordinates X. And L is n-dimensional, and when you restrict it to omega naught, you get 0. So if you just take n equals 1, you can check that you will indeed get 0, because when you apply this one form dy to d by dx, you will get 0. Okay, so because of these terms, you get 0. So we just checked that in R2, R1, like the x-axis, is a Lagrangian submanifold. And in fact, the same is true for any surface, for that matter. You take the surface, then all curves on the surface are going to be Lagrangian. So here you see two drawn surfaces. These are all Lagrangian submanifolds of the surface. Let me call it sigma. So this is L, and so on. All right, so as I said earlier, what we're going to do for our purposes is that we're going to suppress the symplectic structure, and we're going to play around with curves on X. Okay, just to know the Fukaya category, which is quite an unknown, complicated beast, just to know it better and make friends with it. So, but what we need in this is floor theory to exist. And for that, we need unobstructed curves. So this obstruction is basically obstruction to floor theory. And if you only consider unobstructed curves, then if you consider unobstructed curves, then you can form floor theory works, you can use it, and go to the Fukaya category and so on. So you want closed curves. These are basically oriented immersed curves that lift to a properly embedded line in the universal cover, which is R2 of or a square for the surface. And it has implications which are probably important for us, that this excludes null homotopic curves that you can pinch to a point, and also curves that bound an immersed fishtail. Okay, so this is going to give, obstruct this, which we do not want. We want this floor chain complex to be actual floor chain complexes, and we want the differential to be 0. We'll see that later. So floor homology is something important. Why we need to revisit all of this is because floor homology usually involves embedded curves, and we're considering immersed curves. Okay, so we need to go over everything, check everything's fine. And then I told you that we need, when you disregard the area form, you don't have some control on, the sums and convergence. And so we need something extra. And so we introduce admissibility. So if you take two curves, gamma 1, gamma 2 on the surface sigma, these are called admissible if any two chain homology two chain or Euler 0 two chain between these two curves has positive and negative coefficients. So let's see what that means. So you have this green curve here and the purple curve here. You see these two curves, you see they intersect, and you have this yellow region with a plus on it right here. And then on the back, you see another region. And you see that these two regions have, you remember we considered oriented surfaces. And with this orientation, the curves inherit an orientation. With these orientation of the curves, you can define with the help of the signs, the plus and the minus of these regions. And so this is, let's say, plus, and the one that wraps around the back is minus. So when I say it wraps around the back, this is what I'm talking about. This part, and everything that goes at the back, okay? So these two bound a homology, which is like a, you can say a linear combination of these regions, yeah, and with positive and negative coefficients. So what that means basically is that you cannot admit bounding curves that bound a cylinder. So this green and purple curve right here do not work because they only bound one region, which will have either a plus or a minus sign. And so you don't have negative and positive coefficients, okay? So let's look at this blue curve and this red curve. Again, you have regions, you have this region, the plus, maybe this one is a minus that wraps around at the back. And this is basically, again, these are two admissible curves. And the same goes for this light blue and dark blue, or this blue with the yellow, and so on. Okay, so these all give you like different examples of admissible curves. So why do we need it? We need it because it ensures that homotopy invariance of floor homology is intact. This would maybe make more sense when I give you the definition of floor homology. And we need finiteness convergence that, you know, this ensures finite. And that's what we also do. So let's look at the definition. So for any pair of admissible curves, so you start with gamma 1, gamma 2, these are admissible curves, you can define this, let's say, vector space with Z, which is generated over Z by the intersection points between gamma 1 and gamma 2. So you have two curves and they intersect at some points. You take these points, and with these intersection points, you generate a group. And this is graded. You see an I over here. This means that here you have chains which are of degree I, and this is Z2 graded. So you either have a positive odd degree or an even degree. And this degree is again given by the orientation. So if you look at this picture over here, so here you see a positive intersection between two curves. The P is a positive intersection. And to that positive intersection, we always assign an odd degree. So that's the formula. Okay. So the parity is given by, so parity is odd, of the intersection point is odd if you have a positive intersection, and this is even if it's negative. So this is what you call a floor chain group, if you like, in the ith degree. And if you collect all these in all degrees, you can define between two consecutive degrees what we call the floor differential. And it's defined by counting immersed bigons between. So this is what we mean. You have two curves. You have two curves here, right here. You have two curves, gamma 1 and gamma 2. and they intersect in points. And between two intersection points, you have this bigone, a two-sided gone. And these are immersed because you can look at them as, a map from this half disk that you see on the left and going into this surface sigma, okay? So you see the, right here. So it takes this point P and it maps it to the output point Q. And in order to do, while you do that, you've counted this one bigone. And there is a sign which has, contributions from different things like not being oriented here, or the orientation not being in line with the orientation of U itself, and so on and so forth. And you can check that these maps, they square to identity. Okay. So this is really a chain complex. And remember, we said that this is not true if these curves, they bound an immersed fishtail, which is why we also took that out. All right, so what's floor homology? Finally, floor homology is just passing to homology of this chain complex, and you get the homology. That's for any pair of admissible curves. So just to say that if you have a pair, so if you have two curves that are not admissible, then you can always, it's quite a generic condition. You can always make them admissible by just pushing, making a finger move. And so, then you get a positive and a negative thing, and it becomes, so if it, yeah, so it's quite generic. It's not something that we're imposing. It's not something heavy. All right, so next we move to the Fukaya category of the surface. So this is, I remind you, a topological model. And so for instance, here, there is in Abu Zaid's picture, there's going to be some contribution with weights that are given by areas of these disks, the bigones. Okay, so that's a contribution that comes from the symplectic form if we're still considering it, but we're not because we're disregarding the area form, so we just have this simple formula. All right, so what's the definition? So it is an infinity pre-category, which is defined by the following data. You have objects that are closed, unobstructed, immersed curves inside your surface. Morphisms or arrows are floor chain complexes generated by intersection points between these curves. This category admits n tuples of admissible curves without triple intersection. So this is not something that we allow. And so among these transversal objects, you have these higher compositions or higher maps, which is, so you remember something, the differential looks something like this, yeah, going from one complex to the other, one chain group to the other. And in fact, you have so many inputs and going to another chain group. Okay, so that's MK. The differential is just M1, which count under an admissibility condition, which you can extend to many curves. So you remember for the differential, we had this half disk with 2 points here and 2 curves here, and now you have so many points and these curves in between, and they get mapped like this to these intersections between so many curves on the surface. The gammas on the right are curves on the surface, and they intersect to give a k plus 1 gone. And so you have k inputs here and then 1 output, so that gives you a k plus 1 gone. And these maps, they satisfy infinity relations. This is what makes the Fukaya category an infinity pre-category. Okay, so I'm not going to say much about the infinity relations. Maybe I can just show you quickly. So the infinity relations, so first of all, I told you that M1 is just the differential, and it squares to 0. That's one relation. This is basically saying that M2 is a chain map. So if you're familiar with any homological algebra, this second equation relation just reads like M2 commutes with the differential, and that makes it a chain map. And this one reads like this is the associativity of M2, the product map, and in this sequence of maps, and this is associative up to a homotopy, which is this M3, this map M3. Oops, got too dark. Okay. Anyways, I don't, yeah, this is just for the sake of completion. Okay, so we showed that these immersed K+1 gons with convex corners are, rigid holomorphic K+1 gons. So what you see in that analytic picture without suppressing the area form, you get the same thing on this side in the purely topological context, suppressing the syntactic form. But there's a lack of units. I don't think I have time to go about this, but anyways, we say something about these weak identity morphisms that I think skip. So now comes a main result, which is the growth indeed group of the Fukaya category. So we fix a non-singular vector field. So before I do that, we've just managed to define what the Fukaya category is of the surface. Okay, and with the admissibility condition, we've assumed that things are finite. What is finite? This count. You see a count over here. We've ensured that these counts are finite. You can actually make this count, and you can actually you have a number. Okay, so these maps are well defined. All right, so we fix a non-singular vector field on the surface, which means you only allowed only one singularity, which is the small z over here. And you can define a map with the help of this vector field. You can define a map from the Fukaya category of the surface to, so this blue is just the first homology group of the sphere bundle over sigma, which is our surface. But if this is something unfamiliar, you can just look at this splitting that this has. So it's the first homology group of the surface. This is generated by, so depending on the genus, it's generated by these 2G curves. And so let me just draw for the 2G, the genus 2. So you have these curves. So these are called the licorice generators. No, it's just these curves. So these are the alpha curves, and these are the beta curves. Okay, so that's what gives you this homology here, and they generate, and then you have this this quotient, which is Z mod, the Euler characteristic of sigma. So I hope you're already familiar with the Euler characteristic, which maybe you've seen this before for polyhedra is defined like this. So this is the number of vertices, the number of minus the number of edges minus the number of faces, always 2 for polyhedra. And here you can also have a topological definition, which is given by the CW complexes. So you can imagine this sphere as we know it is has a CW complex. So you have a point which is 0 dimensional, and then you have a disk which is kind of joined to this point. You take a disk, you take its boundary, and you scrunch the boundary to this point, and that gives you like a balloon. It gives you a sphere. So you have a point that's 0 dimensional minus nothing that's 1 dimensional plus something that's 2 dimensional. And there's no surprise. This is a topological invariant. No surprise that they match, because if you take this cube and you blow some air into it, its sides, everything gets rounded, it becomes a ball. But anyways, this is what's interesting for us is basically this thing over here. Okay, so the Euler characteristic is 2 minus 2G. At the moment we know RG, the genus of the surface, which means these holes, we fix the G. So this one, for instance, has Euler characteristic, which is 2 minus 2 times 2. It's minus 2. Okay, anyway, so what's the map? The map takes a curve to its class, homology class, and its winding number with respect to this vector. That's where the vectors space, a vector field. So you move along this curve and you calculate the winding number, and that's always a member of this Z mod, the Euler character. So the goal is to extend this to the Grothendieck group of the Fukaya category. And in fact, when you extend this, you can actually show that this is an isomorphism. So just to say what the, so we need to derive the Fukaya category using twisted complexes. So this is just a twisted complex is just, I'm not going to go into too much detail, but just to say that we want to extend it to such a map. So you have a complex of curves. A complex of curves means you have a bunch of curves, and you take the class of that bunch of curves and you take their winding numbers. Okay, and this is how, you know, it's additive. So you take this is just each curve key class and the winding number coming summed up. Okay, so a twisted complex is basically a bunch of curves right here that belong to the Fukaya category, and they come equipped with these intersection points, which are you can consider them as morphisms, and they are this is a closed with respect to the twisted differential. And so this is an infinity pre-category, the twisted category over. So if you take any category, any infinity pre-category, which our Fukaya category was, you can consider the twisted category over the Fukaya category. This will again be an infinity pre-category, but this now it would be a triangulated one. That's why you want to do it. And then so you can define again objects, you can define morphisms and so on. And so what is this Grothendieck group? The Grothendieck group is just the group generated by quasi-isomorphisms of twisted complexes modulo distinguished triangles. So this is the usual way you define it, even in group theory, in algebra. So these are distinguished complexes. So these are two objects. And C is just the cone of a morphism between A and B, if you know what a cone is. And then we have a bunch of facts that we need to come down to the result, which are just interesting in their own right, in the sense that if you take such a curve on the surface, so let's say this is what your surface looks like, and you take this curve, which bounds genus 1 subsurface. This is the gamma. You take its class and call it T. So this T is well defined up to isotropy. So if you move this gamma with, to another curve, which is isotropic to it, so you can move it back and forth, the class remains the same. So T is, independent. If we consider alpha 1, alpha 2, alpha 3, which bound a pair of bands, so this is common terminology. You have this curve over here, and then you have bands. You have two curves here. Okay, so these are two curves that bound, three curves that bound a pair of bands. Okay, so you have three curves that bound a pair of bands. In K0, in the Grothendieck group, their classes, they add up to T, which basically just means that at the level of the Grothendieck group, if you take class in the Grothendieck group, the class of bounding or separating curves belongs to this subgroup that's generated by T. We'll be using this. And then you can look at if you have, right. So next we want to see what maps to this side. You see what maps here. Yeah, if you want to see what goes in this part of the target space under phi, then you can look at this subgroup generated by T, and this isomorphically maps to that side, that part of the morphism phi. You can see this intersection. And this basically uses the fact that you have two curves that bound homeomorphic subsurfaces of sigma, then their class is the same at the level of the growth. Right. Okay, so there's something about relating the cone, because I mentioned the cone here. So something about relating the cone to the surgery, or the connect sum of two curves, or resolving the singularity, this intersection point over here, but let's not go there because I don't have enough time. So we have this theorem. So the Grothendieck group of the Fukaya category is isomorphic to the first homology of the surface and this other summon, which is Z mod the Euler characteristic of the surface. And this phi from K0 to this, as we saw earlier, is already surjective. So the only thing you need to show is that any gamma with trivial homology lies in the subgroup T. So it just goes to 0. And this is what you want to show. So for instance, I have it written up here. So if you have a trivial class for gamma, then gamma will be a linear combination of curves that bound a pair of bands, which means it will fall right here in this subgroup generated by T. And that's what we wanted to show. Okay. So it's as you can see, it just uses, so the Grothendieck group gives you some information about the Fukaya category. The Fukaya category in itself is fairly simple when you just don't look at anything else and just play around with curves on a surface. And I think I can stop here so that we have a couple of minutes. I'm sorry, I should have stopped like 5, maybe 10 minutes earlier. Sorry for going over time, but I think we can stop here.
Oh, that's okay. Thank you very much, Haniya, for a wonderful talk. Definitely, there are lots of technical stuff, but I think you use different colors and try to elaborate the technical detail in a very nice way. Any question from the audience? Okay, Haniya, I would like to clear this this map, the Fukaya category going to the Z to winding number. I think the group you are defining. Yeah, this one. I'm just curious about this second sum, the term which is appearing after the summation, which is Z quotient with the Euler characteristic. So what does it mean? So this is going to be a fixed number, right? So the winding number for any loop is going to be the fixed number, something like that.
Right. It's right. It's going to be an element in this class. That's right.
So why this is being indicated by a class? So Z quotient with the so okay. If I forget about this omega, if one consider about Z quotient with the Euler characteristic of the manifold, this is going to be a fixed number, right? So Euler characteristic is fixed. So this is going to be a fixed number.
Right.
And then afterward, it is going, when you quotient it, so it will turn out to be classes, which are going to be less than that.
Right. So the point is that you can, for all these integers, going up to this Euler characteristic, for all these integers, you can define, you can always find a curve. That's the whole point, that this is already static. You can always find a curve which has that winding number.
Can you show it with some example, maybe for a simple case, how this goes?
So, yeah, I mean, for instance, if you have this, if you look at this around the singularity,
okay,
if you go around with this winding number, it has winding number 1. And similarly, you can draw other curves that so it basically the fact is that what you expect is that it should be the first homology of the sphere bundle of sigma. Is to use this splitting, which is natural in the sense that if you admit a non-singular vector field, say for one singular, which is you can treat that as your base point, then you can map a curve to its class, the homology class, because it's just on sigma, and its winding number with respect to x.
Okay. Any other question from the audience? Thank you, Haniya.
Well, I would like to ask, am I audible?
Yeah.
Yes,
yeah.
yes.
Yes, I would just like to ask, can you please repeat how a complex is twisted?
Right. So basically what we want to do is that, I'm sorry, this is very hurried. So what I want to do is I want to find the Grothendieck group of the Fukaya category. And so the ad hoc definition of the Grothendieck group is that you do it for a triangulated category, where you have this, if you put it very, in very roughly speaking, it admits distinguished triangles. Okay, so we want these distinguished triangles to exist, and so you do it for a twisted. So you do it for triangulated category. The Fukaya category is not triangulated. So we derive it, like you can say, in a sense, we make it slightly more complicated, but it admits distinguished triangles. So what we want to do is we want to consider twisted complexes over the Fukaya category, and this is what they look like. So the Fukaya category had objects which were curves, bunch of curves or curves, and it had morphisms which were given by floor homology, or in fact floor chain complexes. And so you take these bunch of curves from the objects in the Fukaya category, equipped with degree 1 morphisms. So for us, this is morphism is, if you take two curves, alpha and beta, then their intersection point is, you can consider it morphism between going from alpha to beta. Okay.
Right.
And if it's odd degree, which it is in this case, the way I've drawn it, then it's a degree 1 morphism going from alpha to beta.
Right.
So this is, So it's basically deriving the category, like making it a little bit more complicated, but with more, let's say, having more with nicer properties.
Right.
Any other question from the audience?
If I'm allowed, I would like to ask one more question. You briefly mentioned Morse theory. So like everybody should try that, because I just wanted to ask, like in usual calculus, we have the idea of critical points. So does Morse theory would tell us, give us a bound for the number of critical points for our usual functions like x square or, x cube?
Right, that's a very good question. If you look at a function of a single variable, which you are looking at,
right.
Then yes, you apply Morse theory to that, you get the same. And if you look at a function of several variables, then again, you can look at the critical points, and the number of critical points is governed by the topology of the space on which you're defining them and on which the function is defined. So let's say if you have a surface like a torus, then you have a function of two variables, or a smooth function, and then you have so there's a way to so you look at the Hessian and you compute So there's a way to compute the principal points. That's one thing. But Morse theory without computing anything, just if you know the topology of that, say, torus or surface well, it gives you. That's right.
Right. Thank you. Thank you.
Okay. Any other question from the audience? Okay. If this is the case, let us thank Haniya. Haniya, may you please share the reference of your paper, the work you have presented?
Yeah, I don't think I have the archive code written somewhere. I don't think I have it, but I can share the title of the paper, which is it? Yeah, that's what it is. Topological Fukaya category of Riemann surfaces.
Okay. Okay. Thank you very much for a wonderful talk. And definitely,
Dr. Imran, I have one question just come in my mind. Why not you see on the torus these things? On why we have the genus 2 on above surfaces?
Right, that's a very good question. So, you see, the motivation of this was coming from comparing the two geometries. And so genus 1 is, if you look at it as a complex manifold, one-dimensional, it's an elliptic curve. And the case of the elliptic curve is very well, understood. The homological mirror symmetry, everything is kind of set. And if you want to look at other manifolds, the starting point would be surfaces of higher genus. And then you would move up a dimension. So this is all dimension, complex dimension 1. And then you'll move up dimension and so on. That would be my very simple answer.
So what I understand, we cannot define the Fukaya category on genus 1 manifold, like on torus.
No, that's not what I said. So what I was trying to say is that you have you can do Z2 graded. You cannot do, so you could have a different grading, like R was Z2 graded. You could have a different grading, but yeah, so the question is that no, you can. So as I said, that you have already have the it's a symplectic manifold. Again, you consider Lagrangian submanifolds. The Lagrangian submanifolds intersect because they're curves on your torus. They intersect, and they give you. There's a model, for instance, given by Zaslow. There is, but they've like in depth studied the complete homological mirror symmetry. So they don't just talk about the Fukaya category. They also talk about the derived category of coherent sheet. So the goal is to understand higher genus surfaces better, because genus 1 is like it's thoroughly studied.
Okay, thank you.
So,
Haniya, just from the question of Danish, this is a really layman question. When we talk about the twistor manifold, so what is a good example to visualize whether the torus are the good one?
Twistor spaces?
Yeah.
Yeah, I'm afraid maybe we should ask Danish, because I'm not.
No, we cannot define, because the manifold should be 4-dimensional manifold. So torus is a surface, just a 2-dimensional manifold. So when we're defining the twistor spaces, we are taking those which are 4-dimensional manifolds.
Right.
So surfaces are not twistor, right?
Yeah.
Thank you. Okay, if this is the case, let us thank Haniya for a wonderful talk. And thank you very much for the audience for asking the questions and being attentive. So it's time for the new advertisement. Haniya, can you please stop screen sharing? So, okay. So, okay, this is our upcoming seminar. The next seminar is by Hara Bosch, and she is from Aristotle University, Greece. And she will be talking about something related to the curves. Again, continuing. Haniya was talking about something topological. So she will be talking about some algebraic techniques. So some blow up and some other related topics. So the relative canonical ideal for large family of curves, generating sets and Petty numbers. So that talk will be on 23rd May and at the same time. So anyone interested, you can use this link. Again, we will make the announcement. So you can join through these particular links. So you can join the talk by using the link. One more announcement, which is really very important. We have set up a YouTube channel for where we have placed all the recorded talks of the John Conway Spirited Seminar Series. You can access all the recorded talks from our website as well as from the YouTube channel. So even you can download those. So this is an announcement for the interested one who would like to uh, just likes to download some talk from our archive. That's the final announcement. Thank you, everyone. Thank you, Haniya, for your wonderful talk. Thank you very
Thank you.
much. Thank you. Bye-bye. Take care. Allah Hafiz.